Welcome to AP Chemistry. In the previous unit, we discussed calculating enthalpy changes in reference to intramolecular bonding. In this unit, we will distinguish between intramolecular bonding and intermolecular bonding, focusing on the type of interactions possible, and then discuss the types of solids that these will form, as well as their associated properties. The first interaction provided in the list from strongest to weakest interactions is between an ion and a polar molecule, an ion-dipole interaction. Without this type of interaction, there is no such thing as a salt dissolved in solution. Typically, around 6 molecules of water will surround a dissolving ion. But this is not necessarily fixed, with the water molecules able to fluidly pass around, breaking interactions from a jostle here and there, and again reforming immediately with the ion. But in such a state, the ion is constantly attracted to the polar molecules surrounding it. In a state that's called aqueous, that polar molecule is water, as shown. You should note that the electropositive end of the dipole, in this case the hydrogen end of the water molecule, will be attracted to anions, negatively charged ions. And the electronegative end of the dipole, in this case the oxygen end of the water molecule, will be attracted to cations, positively charged ions. Now, it may be intriguing to consider that in order for salt to dissolve, the polar substance must actually overcome the lattice attraction holding the ions together. Of course, this is also driven in part by the new attractions and release of energy that is possible between each individual ion and the polar molecules. But this lends itself to understanding the basis of a trend. That is, that salts with high lattice energies will tend to be insoluble in solution, whereas salts with lower lattice energies will tend to be soluble. The next interaction provided is called hydrogen bonding. Please note, hydrogen bonding does not refer to the localized covalent bond in the hydrogen molecule. It is not even possible between hydrogen molecules. Rather, it only occurs in reference to species that have either a HF, HO, or HN covalent bond. Now, in order to understand why this interaction occurs, let us return to analyzing the intramolecular bonds first. The reason why any HF, HO, or HN bond is special has first to do with fluorine, oxygen, and nitrogen being the most electronegative elements on the periodic table. And not only does hydrogen have a lower electronegativity, but also hydrogen has only one valence electron. This means that when a bond occurs, there is an extreme dipole in which the lone electron of hydrogen is essentially pulled away, and on the hydrogen end of the dipole, there exists a kind of pure positive electric charge. It is this site that allows for hydrogen bonding. If another substance that contains fluorine, oxygen, or nitrogen is nearby, this hydrogen end will be intensely attracted to any one of these, and it is this attraction that we call a hydrogen bond. Let us then look at a sample of pure water, first in its crystalline solid state, then in transition from the solid to liquid state, and then finally in its pure liquid state. You should immediately see all the possible hydrogen bonding that is occurring here. Of course, hydrogen bonding is most evident in the solid state. This is because the hydrogen bonding in the liquid state is significantly weaker due to the more kinetic energy available to our system. There's also an energy cost to transition from the solid to the liquid state, called the heat or enthalpy of fusion. Fusion here is Latin for to melt. It is the kinetic energy required to overcome the hydrogen bonds just enough so that the particles can move past each other, costing in this case about 6 kilojoules per mole. Now view the transition from liquid to gaseous state, and finally the gaseous state itself. Note that the enthalpy of vaporization is significantly higher than the enthalpy of fusion. This is because there are no hydrogen bonds in the gaseous state. That is, in order to transition from the liquid to the gaseous state, all hydrogen bonding, and that is, all interactions, must be overcome. Here, the energy cost is much more significant. In the provided graph, we can clearly see how HF, H2O, and NH3 do not follow the trend of boiling points in progressing down a group. Again, this is due to the strong hydrogen bonding that occurs in these substances. For a hydrogen bond is about 5% of the strength of an average covalent bond. As you probably have already learned, liquid water is more dense than solid water. This is not typical for substances. But this property allows ice to float in liquid water rather than sink. This is clearly due to the hydrogen bonding that occurs in the solid state that forces the water molecules into a tetrahedral like conformation, which ends up taking substantially more space than the liquid state. Hence, the ice floats. Without this property, glaciers would fall to the bottom of the ocean, thereby destroying the protection they provide for our planet by reflecting enormous amounts of light back into space. Lakes and all bodies of water in the winter would freeze from the ground up, destroying all life on the bottom floor. And the evolution of life would probably have never occurred, for hydrogen bonding allows water to function as a universal solvent. And among DNA molecules, hydrogen bonding stores the code of life on planet Earth. The next interaction provided is called a dipole-dipole interaction, occurring between two polar molecules. That is, between the opposite electrically charged ends of the polar molecules. Here we can envision any polar molecule having this type of attraction. As long as the molecule exhibits a dipole moment, the substance will have this interaction. Now, measurements of dipole moments are usually given in the units of debye's. Construct Lewis structures for the substance at the top to see how their dipole moments differ. Note how the stronger interaction correlates to a much higher boiling point. Continuing on, there are two other interactions which you should be absolutely aware of, but nonetheless are not commonly referred to since they are possible only in certain types of mixtures. That is, an ion-induced dipole and a dipole-induced dipole. The first interaction is between an ion and a nonpolar molecule, and the second between a polar and a nonpolar molecule. In the first case, the ion induces or causes a polarity to arise inside the nonpolar molecule. In the second case, it is the polar molecule inducing the dipole in the nonpolar molecule. The point here is to recognize that although a substance may be nonpolar, that does not mean some kind of polarity cannot be created or induced from another electrically charged source. We call this type of polarity that has been induced an instantaneous dipole. With such instantaneous dipoles, we are now ready to decipher our last important interaction, called London dispersion forces, or simply dispersion forces. This attraction is possible between any covalently bonded substance, but we become most acutely aware of its effects when we consider the case of nonpolar substances. Here, we can envision a system of CO2 molecules. You should be aware by now of the existence of dry ice or carbon dioxide in the solid state. If CO2, being nonpolar, is able to exist as a solid, then there must be some kind of interaction possible between the molecules that is holding them together. Things do not simply freeze together by us simply slowing them down. According to such a logic, anything that moved slower, like you, would begin to become stuck to something else moving slower, like your chair. But of course, this does not happen unless some kind of interaction between your bottom and the chair could take place. In order to determine the reason for this type of interaction, we must understand that any solid crystalline state arises out of some kind of electrostatic interaction between the particles that make up that solid. There is simply no solid or liquid state without any electrostatic interactions. And yet, viewing the table provided, it is evidently clear that we can freeze all of these substances. So, what is going on here? At any point in time, electrons are randomly polarizable, and the greater the number of electrons within a given particle, the greater its polarizability of electron clouds is. When this random instantaneous dipole occurs, it is capable of inducing another dipole in an adjacent particle. Thus, dispersion forces are literally an instantaneous dipole induced dipole interaction. To understand the implications of such an effect, one must consider that all of these possible random interactions are occurring dispersively among billions upon billions of these particles. It is not one simple interaction which creates the effect, but the interaction multiplied upon an order that is, from our viewpoint, unfathomable. And yet, this is not physically unobservable. We can see during special laboratory conditions, in the absence of gravity, the effect is clearly evident among larger, nonpolar particles. Since dispersion forces are first dependent upon the number of electrons in a given substance, comparing molar masses between substances is a quick and convenient way to tell the strength of their dispersion forces. However, if one cannot distinguish the strengths from this, then one should compare the surface area between the substances. The greater the surface area there is, the greater the possibility of dispersion force interactions. Finally, you should note that when comparing substances after you have identified all possible interactions, that stronger attractions will correlate with higher melting points, synonymous with freezing points, which is the temperature at atmospheric pressure to transition from the solid to the liquid state, higher heats of fusion, synonymous with enthalpy of fusion, which is the kinetic energy required per mole to transition from the solid to the liquid state, higher boiling points, synonymous with condensation points, which is the temperature at atmospheric pressure to transition from the liquid to the gaseous state, higher heats of vaporization, synonymous with enthalpy of vaporization, which is the kinetic energy required per mole to transition from the liquid to the gaseous state, higher viscosity of fluids, which refers to the ability of a substance to resist flow, and lower vapor pressures, which is a measurement of the pressure of the vapors generated from a given substance in the solid or liquid state at a given temperature. Be sure to become absolutely familiar with these as a means of indirectly measuring the strengths of intermolecular attraction.